Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit 9, Lesson 1 on square roots and cube root functions. Now we've talked a lot about roots in this course and we've even looked at both square roots and cube roots already, especially when we took a look at fractional exponents. We're going to be doing all of that and more within this unit as we really kind of drill into functions that are based on roots. Today we're going to be primarily looking at square roots and cubed roots, but we'll be seeing other types of roots as well as we go through this unit. All right, let's jump right into it. Square and cubed roots. Reversing the process of raising a number to a certain exponent is an important process, and that's what square roots and cubed roots do, right? They reverse the squaring process and the cubing process. Two primary examples of this are when we try to find a square root and a cubed root of a given number, right? And again, the whole idea, right, behind square roots and cubed roots, they're kind of like logarithms, right? Great, that'll help you. Is that we are always trying to find a number that when squared gives us 100, or that when cubed gives us 8, etc., etc. So let's take a look at exercise number 1. Without using your calculator, evaluate each of the following square or cubed roots. All right. Now, this should be pretty easy. Pause the video right now and go ahead and do letter A and letter B. Now, obviously, the square root of 100 is 10. That's simple. That's no problem. That's equal to 10. And of course, the reason why is because 10 times 10 is 100. Likewise, a little bit more tricky, I think, for most people is something like cubed roots, because now you have to think about what times what gives me 8, right? But these are nice numbers, and that ends up being 2, right? 2 times 2 times 2 is 8, and therefore it's the cubed root of 8. Now let's take a look at C and D. Why don't you pause the video and see if you can figure those out. All right. Letter C says the negative square root of 49, and that's negative 7. Now, keep in mind, one of the larger confusions, right, that arises with square roots is very understandable, right? I kind of skipped right over it when I looked at letter A, and we talked about the square root of 100 being 10. Obviously, 10 times 10 is 100, and negative 10 times negative 10 is also 100. So even though the square root of 10 has two values, both positive 10 and negative 10, we need a way of distinguishing between the two, right? This is simply the positive square root of 100. This is the negative square root of 49, all right? So we're going to distinguish between the negative square root of a number and the positive square root of a number by simply whether or not there's a positive or a negative out front of the radical symbol. We don't have the same problem with cubed roots, right? Because negative 2 times negative 2 times negative 2 is not positive 8. So the square root of 8 in terms of real numbers is only positive 2. Now, in letter D, we have the cubed root of negative 64. Now that's perfectly okay because negative 4 times negative 4, right? Negative 4 times negative 4 times negative 4 is negative 64. So the cubed root of negative 64 is negative 4. I don't need a negative or a positive out front because, again, there's only one number that's true of. Now, we looked at earlier in this course how fractional exponents are equivalent to roots. So here, when we have 121 to the 1/2, 125 to the 1/3, negative 1 to the 1/3, and negative 81 to the 1/2, right? In all of those situations, we've got a square root, a cubed root, and a square root. So why don't you go ahead and pause the video now, and if you need to put it in terms of roots, please do, but don't use your calculator. So 121 to the 1/2 is the same as the square root of 121, and that's 11 because, again, we're talking about the positive version. 125 to the 1/3 is the same as the cubed root of 125. 5 times 5 times 5 is 125, so that's equal to 5. Negative 1 to the 1/3 is the cubed root of negative 1, since negative 1 times negative 1 times negative 1 is negative 1. The cubed root of negative 1 is negative 1. And this one, right, remember, exponents come before multiplication by negative 1. So this is negative square root of 81, and that's equal to negative 9. All right, great. Now, one thing that you may have noticed about all of these, and we're going to address this in the next problem, is that anytime I had a square root, I always had a positive number under the square root, okay? What's known as the radicand. Don't worry about that terminology. All right, but the number under the square root was always positive, but that wasn't always the case with cubed roots. So here, the number under the cubed root was negative, and here, the number underneath the cubed root was negative. So let's explore that just a little bit more in exercise number 2. An important idea, exclamation point. There's a very important restriction on numbers we can find square roots for that is not an issue when finding cubed roots. So, exercise number 2. Why is the cubed root of negative 64 a real number, but the square root of negative 64 is not? All right, well, I want you to play around with this a little bit, think about why that's true, and then we'll have a discussion of it. Pause the video now and consider that a bit. Okay, well, with cubed roots, right, we're always looking for a number that when multiplied by itself 3 times, i.e. cubed, gives us a negative 64, or some negative number underneath there. So the cubed root of negative 64 is equal to negative 4, because negative 4 times negative 4 times negative 4, and again, make sure you really get that right. You know, if I did this first, I'd get 16 times negative 4. That would be negative 64, right? So that's perfectly okay, right? In other words, if I cube a negative number, so cubing a negative number, cubing it, not cubed rooting it, but cubing a negative number gives a negative. But now let's consider the square root of negative 64, right? The square root of negative 64. Well, you know that the square root of 64 is 8, because 8 times 8 is 64. Now you might say, well, maybe the square root of negative 64 should be negative 8. But, you know, negative 8 times negative 8 is positive 64. And 8 times 8 is positive 64. So neither of those are correct. So what else would it be, right? And the plain fact is we cannot take the square root of a negative number, because whenever we square a number, I should say, a real number, the result is not negative. So whenever we square a real number, the result is not negative. I think we've talked about this before. I would love to be able to say whenever we square a real number, the result is always positive, and then somebody would get on my case because of the number 0. 0 times 0, which is very legitimate, is equal to 0. And 0 is neither considered a positive number or a negative number. So, you know, I could say whenever we square a real number, the result is positive, parentheses, except for 0. But I don't even want to go there. So whenever we square a real number, the result is not negative. So there's really no way to find the square root of negative 64. In other words, the number that when multiplied by itself gives me negative 64, because all the numbers that we know about when you square them gives us a result that is not negative. All right, so that's critical. Later on in this unit, we're going to relax that a little bit, and we're going to introduce a brand new type of number that when you multiply it by itself does turn out to be negative. But don't worry about that for now. Let's talk about graphs of square root functions. We can create functions with both square roots in them and with cube roots in them. Keep in mind that whether the output of a square root function is positive or negative will be specified in the formula of the function. All right? So let's take a look at exercise number 3. Consider the functions f of x equals the square root of x and g of x equals the square root of x plus 4, then minus 3. Letter A. Create a table of values that allows you to plot f of x and then graph it on the grid provided. All right, so this particular function f of x, I want you to be able to graph without using your calculator by being able to create a very simple table of values. So what do? Well, let's throw down a little xy table, and let's think about numbers that have nice square roots. Okay, keeping in mind, of course, I can't put any value of x in that's negative. If you're confused about that, please see exercise number 2. All right, what I can certainly do is I can certainly take the square root of 0. And the square root of 0 is in fact 0, right? 0 times 0 is 0, so the square root of 0 is 0. I get some students that say, well, you can't take the square root of 0, which I find very weird because 0 times itself is 0. Now, I can also very easily take the square root of 1. And just like 0, the square root of 1 is itself 1. The square root of 2, though, is an irrational number. It's about 1.414. The square root of 3 is also an irrational number. It's about 1.732. All right, so I'm not going to write those down. But 4 is nice, right? The square root of 4 is 2. 5, 6, 7, and 8 are also numbers whose square roots are irrational. But then the square root of 9 would be 3. The next nice one would be 16, and it would be 4, etc. All right? So I can use those points to graph the fundamental parent square root function. Pause the video and do that really quickly. All right, so simple enough, right? I get that beautiful kind of half parabola, right? Literally the inverse of y equals x squared, or at least part of its inverse. All right, let's take a look at letter B. How would the graph of f of x need to be transformed to produce the graph of g of x? Graph g of x based on your answer. All right, so cool, right? We just got done with a unit on transformations. So I should now be able to look at the formula of g of x, compare it to the formula of f of x, and talk about what transformations have occurred. Pause the video now and see if you can both describe the transformations and then use those transformations to map where all of these points go on the function g of x. All right, well, the fact that we added 4 to the x before anything else is done means we're going to shift our function 4 units to the left. Because we've then subtracted 3 from the overall function, we're going to be shifting the function down by 3 units. So 2 transformations, right? A left shift by 4, and then a downward shift by 3. And the beautiful thing now is I can literally take every point on this graph, like 0, 0, I can shift it to the left 4 and down 3. Then I could take this point and shift it to the left 4 and down 3, etc. Pause the video now and go ahead and get a good graph of g of x on the same set of axes. All right, here we go. Right, simple enough, there's our g of x. And again, all we're really doing is taking this point and going 1, 2, 3, 4, 1, 2, 3, taking this point, 1, 2, 3, 4, 1, 2, 3, etc. Just shifting it like that. Awesome. The whole point of a parent function, the whole point is to take a function that's very simple and then take a function that's based on that and be able to graph it and think about its behavior based on the original. Letter C. For what values of x is the function g of x defined? Now, this is basically saying the same question as what is the domain of g of x? So this is really asking for the domain of g of x. All right, well, how would you describe the values of x for which we can get a function value out for just the red curve? Pause the video now and see if you can write that down. All right, well, there's no graph out here, right? There's no way for me to put in any values of x that are to the left of x equals -4. And yet, any value of x from x equals -4 to the right gives us a value for the function. So it's defined for all values of x such that x is greater than or equal to -4. Or, if you like interval notation, you'd say -4 to infinity, and you'd have the square bracket on the -4 because the function is definitely defined there, right? G of -4 is equal to -3. And then it extends out to infinity, but of course we can't include the infinity. All right, let's keep going. Cubed root graphs. Now, you've worked a lot less with cubed roots than you have with square roots. That's just the plain fact. So the cubed root function is likely unfamiliar to you, right? You probably didn't graph that in Algebra 1, whereas you certainly graphed the square root function. So let's take a look at the cubed root function and a transformation of it in exercise number 4. Consider f of x equals the cubed root of x and g of x equals 4 times the cubed root of x. Letter A. Without your calculator, create a table of values that will allow you to graph f of x, then graph it on the grid provided. All right, so just like before, what we want to do is we want to come up with some values of x, right, that have nice cubed roots. Okay. And maybe part of the way you do that is thinking about the cubing process. Like for instance, 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, 3 cubed, whoops, 3 cubed, that does not look like a cubed. 3 cubed is 27. But already we see that 3 cubed, right, equaling to 27, that's too big. Right? Now, when I say I'm cubing all these, I want to go backwards, right? So in other words, 0 and 1 are still not interesting, right? 0, the cubed root of 0 is 0. The cubed root of 1 is 1. And the cubed root of 8 is 2, right? So all those help. Now, unlike the square root function, we can actually also have negatives here, right? So I could say, well, how about -1? Well, the cubed root of -1 is -1. And I could also have the cubed root of -8. That's going to be -2. The next two that would be natural to put in would be the cubed root of 27, which would be 3, and the cubed root of -27, which would be -3. But at least on our grid, those two would be too big because we simply don't have x values at 27 and -27. Use this table of values. I know that the x's aren't in order, but that's okay. Use that table of values to produce a cubed root of x graph. It will be very short, right, because the y values are very small. All right, so this is going to give us a graph that kind of looks like that, right? It's really quite cool, right? We have -8, -2, -1, -1, 0, 0, 1, 1, and 8, 2. Awesome. So now let's keep working transformation work. Letter B. How will the graph of g of x compare to that of f of x? Use this to plot g of x on the same grid. Label both functions. All right, so g of x is 4 times the cubed root of x. In other words, it's 4 times f of x. How will it compare? What transformation just occurred? Pause the video and see if you can answer that question. Well, this is a vertical stretch of f of x by a factor of 4. So let's write that down. It is a vertical stretch of f of x by a factor of 4. Now, one thing that you could do, right, is you can simply come to your graph, and everywhere there are nice points, like here at -8, -2, you could now make it -8, -2 times 4, so that would be -8, -8. right? Here where we have -1, -1, we would then be at -1, -4. Or, if you wanted, you could create a table of values where you essentially took this table, right, and you left all the x values alone. Remember, we're not doing anything horizontally here. And you would just take each one of those y values and multiply it by 4 to get a new table of values, right? We're just taking all the original y values and multiplying by 4. Go ahead and use that to then plot g of x. Excellent. All right, let me just kind of bring this back up here. And we get a vertical stretch, right? All we've done is taking our graph in blue and we've kind of stretched it by a factor of 4 across the x-axis. All right. Let's take a look at another one. Now, sometimes you're going to deal with cubed root and square root functions, and you don't have to just do it all by hand. Let's take a look at exercise number 5. Find the solution to the equation square root of 6 minus x equals -2 times the cubed root of x. Round to the nearest hundredth. Produce a graph that justifies your answer. All right, so this equation you have no algebraic ability to solve yet. All right, in our next lesson we will look at how to solve some equations that involve square roots in them. All right, but for now, right, to solve an equation where you have a square root equal to some expression with a cubed root in it, the only real way to do it is graphically. So I'd like you to pause the video right now and see if you can find the one and only solution to this equation graphically. Pause the video now. All right, well, let's play around with it. You know, it can be kind of a challenge if you don't have a great sense for sort of what your window should be. So let's add a graph and let's experiment. Right, what I want in the left-hand side is the square root of 6 minus x. That's easy enough. Now the cubed root is a little bit harder to get to, but we can just go to, and we want specifically -2 times the cubed root of x. Okay. Now, one of the good things about this particular problem is that we can immediately see an intersection point in here. It's a little bit of a challenge, but there is definitely an intersection point within the window that our calculator just naturally produces, right? So the great thing is we can now go into our menu, analyze our graph, go to our intersection, you know, just kind of pull the vertical line to the left of the intersection, pull it to the right of the intersection, right? There's the point where it intersects, -3.885 and I guess 3.144, although I really don't care about the y value. Remember, when I'm solving an equation graphically, not a system of equations, I'm just solving an equation graphically, I graph the left side, I graph the right side as separate functions, and then I grab the x-coordinate of their intersection. So, at the end of the day, what I just want is I want to produce a little sketch. This is all the justification of my work. Right here, I'm going to write down y equals the square root of 6 minus x. Here, I will try to do my best to get this one. Put on the intersection point. This is going to be y equals -2 times the cubed root of x. I definitely want to label my window. I went from sort of -7 to 7. And along the x-axis, I went from -10 to 10. And then I want to label that intersection point, -3.89. You can certainly use the decimal accuracy on your calculator. But then certainly what we want to do is round to whatever they specify. So the actual solution will be x equals -3.89. All right. And again, it's completely okay if you're laying out your solution, its free response and whatnot, in taking that point and basically writing down all the decimal places your calculator gives you and then rounding it to whatever it asks you to do. The larger danger is if you need more decimal places than what it shows, because trust me when I say the actual intersection point has x and y coordinates that are irrational. But somewhere within the settings of my TI-Nspire, and I don't want to kind of dig into that right now, I've set my graph to round all intersection points to 3 decimal place accuracy. All right, which tends to be good enough. Let's go into view full screen, and let's do one more problem. Exercise number 6. Biologists are studying the growth of a population of yeast cells. They model the population using the function n of t equals 5 times the expression t minus 8 to the 1/3 plus 17, where t is the time in minutes since the yeast population has been growing. Letter A. Without using your calculator, evaluate n of 0. What does this value represent within the context of the problem? Awesome. So what I'd like you to do is pause the video right now, substitute 0 in for t, see what you get, and then try to interpret what that answer tells you. All right, well, let's do it. Let's figure out what n of 0 is. So n of 0 is going to be 5 times 0 minus 8 to the 1/3 plus 17, which is 5 times negative 8 to the 1/3 plus 17, which is equal to 5 times the cubed root of negative 8 plus 17. The cubed root of negative 8 is negative 2, so I've got 5 times negative 2 plus 17, negative 10 plus 17, and that means n of 0 is equal to 7. Again, I like having you do that by hand. Obviously, the calculator can do that, right? If you were on a test or something like that, it's hardly ever going to be the case that they're going to say, well, don't use your calculator, okay? But there are certain tests where you can only use your calculator on part of it, like some of the AP exams, things like that. Plus, the plain fact is, we want you to be able to think about things like the cubed root of negative 8 without having to use that calculator. Now, what does this represent? Well, obviously, it's the y-intercept because it's the output when the input is 0. But more importantly, right, the input is the time since the yeast population started to grow. N is the number of yeast cells, so it represents the initial number of yeast cells. All right, the initial number of yeast cells. Now let's take a look at letter B. Sketch a graph of the size of the yeast population on the axes given for 0 less than or equal to t less than or equal to 20. Indicate the scale on the y-axis. All right, now we could talk about transformations. We could talk about a vertical stretch by a factor of 5 and then a vertical shift upward by 17 units. But I certainly actually think you should use your calculator on this. So grab those TIs out or Casios or whatever you're using. Throw this in as your first function. Notice, right, we want it from 0 to 20 along the t-axis or x-axis. What you have to decide on is an appropriate y-axis to make it look good. Pause the video now and see what you find. All right, well, this is definitely one of those ones where you want to kind of play around with the window. So let's take a look at that. Let me kind of exit here. I'm going to open up a new doc, go into my graphing, and I'm going to put in 5 times x minus 8 raised to the 1/3 plus 17. Awesome. There it is. I don't even know what that is. I'm going to go in. I'm going to modify my window. I definitely know that I want 0 to 20 along my x-axis. All right. I still don't know what I want along my y-axis, so I'm just going to do that. Boy, that looks terrible. But of course, I know that the minimum y value is 7. So, you know, I might as well like futz around with that a little bit more. I don't know exactly what it should be, but I'll go like, let's say 0 to, I don't know, 20. And that gets me closer, but notice even at this point, right, I'm missing a lot. I need to see stuff up here. So I want to make my window even bigger. I'm going to go into Windows settings yet again. Maybe I'll go up to 40. Ah, that looks much, much better. Now I might make it look a little bit better if I don't go all the way to 40, and in fact what I ended up doing is I ended up going just to 30. Not that 40 would be bad. You know, if somebody had stopped at 40, that would be completely fine. I just really like the graph to take up the majority of the screen, right? And here's a great, a great view of it. We're starting off at 7, right? We're kind of increasing very quickly. We hit some kind of an inflection point, and then we continue to increase, but at a slower rate. And we end up getting some kind of a diagram like that, and including one of the final portions. All right, so I in fact have part of the graph for letter C. So let's take a look at that. Letter C. Biologists would like to know all times during the interval 0 less than or equal to t less than or equal to 20 when the yeast population is at least 22. Write an inequality that models these times and solve it using your graph. All right, well, I already have my horizontal line y equals 22 sitting there. But what I'd like you to do is first write down an inequality that models what they're asking us to find, right? And then see if you can solve it for some time interval using your graph. Pause the video now. Awesome. Well, I want it to be, the yeast population to be at least 22. Which means I'm looking for 5 times t minus 8 to the 1/3 plus 17 to be greater than or equal to 22. All right, greater than or equal to 22. Now, a great way to solve that graphically is to graph the horizontal line y equals 22. Now we can see that the yeast population is at or above 22 for all time values from this point to the right, right? So we're really looking kind of like for this. Now, the way that we can do that is to come into our graphing calculator, menu, graph entry edit, function. I can put 22 in. All right, I get that beautiful like horizontal line that we saw on the graph before. Now what I want is I want that intersection point, menu, analyze, intersection. And what I find is a very nice answer here. No irrational numbers whatsoever. Right? That's intersecting at 9,22, meaning that after 9, I think the time units here are minutes. After 9 minutes, right, we have a population of 22, and every time after that, we also do. So on our graph, right, we would want to have all of this. We'd want to label our intersection point 9,22, and then we'd simply say, right, that t is greater than or equal to 9 minutes. And that's it, right? Now, it's very important for you to be able to take kind of like phrasing like this and model it using an inequality. We're primarily in this course going to be solving those inequalities graphically. All right, let's wrap this up. So today we kind of reviewed the basic notions of, how to evaluate a square root and a cubed root, why you can take the cubed root of a negative number, but you can't yet take the square root of a negative number. And we also reviewed the fundamental graphs of square roots and cubed roots, the way that they look. And then, of course, we had some application problems with them at the end. This entire unit is going to revolve around roots. How do we simplify them? How do we evaluate them? How do we eventually find the square root of a negative number? All of that is going to come in this unit. But we want to lay that foundation by really understanding square roots and cube roots before we do anything else. All right, for now I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.